So the idea we're talking about here is a thing called a geometric or Euclidean vector. That is a vector designed for describing things in Euclidean space, where Euclidean space is a fancy way of saying Cartesian space, which is a fancy way of saying rectangular space. Just points and lines, as it were, where a vector is going to be represented by a directed line segment or ray, where if we're going from P to Q, it's just a line segment from P to Q, from the initial point P to the terminal point Q. And it's kind of interesting to talk about the history of this stuff here, because the idea of a vector is actually fairly recent. That an Italian mathematician named Bellavitis in the 19th century didn't so much come up with the idea, as it were, but what would become a vector is kind of attributed to him, where the more formal definition, the more formal representation, and the name itself, vector, is accredited to the Irish mathematician Hamilton, William Rowan Hamilton, that is. And for those of you who are wondering why I keep talking about math history here, I do think it's important to bring this stuff up, both because it adds some more richness here, adds a bit more context to know that someone was working on this less than 200 years ago, and that one thing kind of came directly as a result of the other. And in particular, Hamilton's work in talking about vectors was built to discuss ideas with complex numbers. So there's a natural connection there, that Hamilton's definition of a vector came about because he was trying to make descriptions of complex things in three-dimensional space, values called quaternions that you don't need to worry too much about right now because that's way above your pay grade, but it is kind of nice to see those connections being built, especially when we're going to talk about the operations for vectors, and they work in very similar ways as rectangular complex numbers. But it's also nice to see this stuff because without it, math sort of becomes a collection of facts that happen to you as presented in books that were somewhere between ordained by God and written down by some men in togas thousands of years ago, which at this point might as well be God, for how attainable their perspective is today. When math really is something that anyone can do.
Not everyone can become a great
mathematician,
but a great
mathematician
can come from anywhere.
And that everyone has the potential to work on if they want to give it their time, and that is constantly changing, that we can have great new developments that fit in with stuff that happened thousands of years ago at the same time as people having telephones, which I think really humanizes the whole subject and brings it back to earth a little bit. But anyway, this idea of a vector to represent that directed motion, that directed change from one place to another, usually we denote with lowercase letters like that, where in print they're written in bold, but because you can't write in bold, we usually notate it with a little arrow over the top. And when we talk about these vectors, we have some basic ideas that we can see here, where we have that two vectors are equal if they have precisely the same magnitude and direction, like so, where the magnitude of a vector is just the distance it's meant to travel. Here we can see that these are essentially parallel rays. And we can have things that are not equal for a few different reasons. For one, we can have ones that look like they should have the same magnitude, but one's just a bit tilted, so they have different directions. We can also have things that look like they should be exactly the same, except one goes in the other direction. And then we can also have things that go in the right direction, but don't have the same magnitude. Because when we're talking about vectors, we're not talking about magnitude or direction. We are very specifically talking about a thing that has both a place it is going and an amount coming with it. We're talking about magnitude and direction. Those are the defining properties of a vector. And in order to get ones that are equal, we kind of do need something like parallel lines. We need to see that they have the same slope and cover the same distance. So, for example, if we want to show the vectors graphed below are equal, that is, we want to show the vectors u and v, where u goes from negative 5, 2 to negative 2, 6, and v goes from 2, 2 to 5, 6, are equal. What we have to do is find their magnitudes and their directions. That is, find the distance they cover and the slopes that they have to get there. So, to find the magnitude for u, which we denote with 2 vertical bars, because it's not just an absolute value, it's a specific vector value that we're looking at there. But that magnitude has the same sort of meaning as the modulus from our last section, really, as what we're looking at here is just the distance covered. Where this distance, not the nicest in the world because we're going from negative 5 to negative 2, but it would be something like negative 2 minus a minus negative 5 squared plus 6 minus 2 squared, where pull these terms together, simplify, take some squares, and we will get 9 plus 16, or 25. Root 25 is just 5. Similarly, for v, if we want to get the magnitude of v, we want to find out how long it is, we use the distance formula again, where the magnitude of v will just be a little bit nicer, but same rough idea. 5 minus 2 squared plus 6 minus 2 squared. Hey, it's the same term as the other one. And it goes to the same place. 9 plus 16 underneath a square root is the fanciest of ways to write 5. Meanwhile, if we want to find that their directions are the same, we just need to check their slopes, where the slope of the value u, it's not quite nice notation, but we're going to have to be a bit brief here, would be y1 minus y2 over x2 minus x1, or excuse me, y2 minus y1 over x2 minus x1. Need to be consistent with that, otherwise I'll get the wrong value. But that would be 6 minus 2 over negative 2 minus a minus 5 for a slope, in this case, of 4/3, while on the other hand, the slope for v, following the same kind of formula, rise over run, that hopefully you may remember even if you haven't seen it in a little while, would be 6 minus 2 over 5 minus 2, which is an equally fancy way of saying 4/3. So, the slopes are the same, the magnitudes are same. That means we have vector u is equal to vector v. That's how we can show equality in this way, where we don't have a whole lot of information except for the space that they cover. As we're going further, we're going to talk about some operations that we have here, and then we're going to talk about how we can more carefully define these vectors so that every time we want to check equality, well, we don't have to chase around these old formulas, at least not every time.